This is Physics 30, Chapter 1, Lesson 6. We're going to think about an example to start. We have a little banana cannon down here in the left, and we've got a monkey hanging from a tree in the top right. Assuming that the monkey is going to let go of the branch at the exact moment that you fire your banana cannon, where should you aim the cannon in order that the monkey will be able to catch the banana? You can think about this for a second, and then continue the video when you have an assumption. Where should you aim to hit a monkey with a banana? If they are released at the same time that you fire the banana at the exact moment the monkey releases the branch, you should aim your cannon directly at the monkey when it's hanging from the branch. As the monkey falls, the arc of the banana will actually meet it in that exact same position. Why is this, you might wonder? It's due to gravity. Gravity is, again, a constant. So that means at the same rate that it's slowing down the arc of the banana, if there was no gravity, the banana would fire in a perfectly angled line. But we can see because of gravity, it has this parabola shape to it. And the same rate that the banana is slowing down is the same rate that the monkey will be speeding up because of gravity. So you should aim directly at the monkey. But what if the banana cannon is really slow, really low powered? Well, the same principle applies. The acceleration due to gravity will just have longer to speed up the monkey and longer to slow down the banana. But again, it's the same rate, so your banana will still hit the monkey if you still aim directly at it. That is, directly at where it is at the beginning of the scenario and not where you think it will end up. Briefly reviewing the components of a vector. We want to know what are the vertical and horizontal components of this vector, assuming it's at 30 degrees. You can pause and solve this here really quick. We did this a couple lessons ago, and then continue when you have an answer. Going through this pretty quickly, we have that x will be 17.3 meters per second and y is 10 meters per second. That is because, again, x is the vector cos the angle, and y is the vector sine the angle. We're going to use x and y components of vectors when we talk about anything involving projectile motion, which is what we have here. A soccer ball is kicked at an angle of 30 degrees to the ground at a speed of 20 meters per second. Calculate the time the ball is in the air, the maximum height, and the distance the ball is kicked downfield. So when we draw this example, 20 meters per second at 30 degrees, it's really important to recognize that this triangle drawn only represents the moment the ball is kicked. It does not represent the overall path of the ball, only that initial moment. We're going to watch two videos here quickly.
Make him think pass, instinctively draw in there.
Talking about Janikowski now in the warm-ups. Just happened to be looking, and so were our cameras. Look at this thing. Hey, goodbye. Now, that's good. Fans down there in the end zone loved it. His career long, by the way, in a real game, on a real kick, is 61 yards. He was 4 out of 7 last year from 50 plus. And this is going to be a 63-yard field goal attempt, which would match the longest in NFL history. Sebastian Janikowski from 63 kicks on the way. It is good. He got it. Wow. NFL history tied here in Denver.
So this first video shows Sebastian Janikowski kicking a 63-yard field goal, which at the time matched the record for the longest field goal in NFL history. Since then, the record has been broken a couple of times, and this kick is now ranked 5th in the longest in the world. The current record held by Justin Tucker at 66 yards. But at the beginning of this video, we saw Sebastian Janikowski kick a 70-yard field goal during a practice.
Hugh Jackson says I gave him a shot. And he made it. How about that?
So usually a lot of field goal kickers, they line up and they take 3 steps back.
In this video, we're going to see David Beckham try to match the world record kick that we just saw in the other video.
There it is. Yeah, we can sign him up right now with his contract.
So this is the record.
This is the record.
I'm not sure with this wind I'm going to make it.
I think that's it. Oh!
It's a long way.
It's
Let me try
it's
the
a
other way.
long
Let
way.
me try this way. With the wind. So that's going to have to go over the crossbar. Will it be about here?
There it is. Oh! Shit. I think we should give it to him. I think we give him the record.
Continuing on, before we do anything or make any calculations, we need to find the x and y components of this initial moment. So we can calculate x to be 17.3 meters per second, and we can calculate y to be 10 meters per second. Now, we want to think strictly vertically. If we forget about the horizontal, because when you kick a soccer ball at an angle, it has some vertical component of its flight and it has some vertical component of its flight. That's what we found here with x and y. So thinking strictly vertically, the ball will go up, at some point it will stop and then start to come down. So at the maximum height, the velocity, thinking only vertically, would be 0. It stopped going up and it's about to start coming down. So we can use this kinematic equation. The final velocity will be equal to the initial velocity plus acceleration times time. Again, thinking strictly vertically, we know the final velocity will be 0, and the initial velocity is 10 meters per second because we're only thinking about the vertical part, we're only thinking about y. Acceleration would be due to gravity, and it's slowing down the ball, so it would be negative 9.8, and we can calculate for t. So we'll find that t is 1 second. Now again, this is only the portion of the example where the ball goes up, so doubling that for time coming down, the total time the ball is in the air is 2 seconds. Now, still thinking vertically, how high did it go? Well, we can use one of our other kinematic formulas, this one, that the displacement, and I've denoted it by displacement v, meaning the displacement vertically, will be the initial velocity multiplied by time plus 1/2 acceleration time squared. Plugging in the things we know initial velocity vertically is 10. We know that the time going up is 1 second. And we know that gravity will be negative 9.8. And again, time is 1 second. Notice that because we're looking for the point that the ball is at a maximum height, we're only dealing with the time going up, so it's only 1 second. We're not accounting for the time coming back down. So the vertical displacement is 5.1 meters, meaning the ball went up to a maximum height of 5.1 meters. Switching our mindset over now to think horizontally, how far did it go? The one constant when we change from thinking vertically to thinking horizontally is time. Time needs to be the same for both things. So when we think about horizontal displacement, denoted here by dh, it will simply be velocity times time. This comes from the same thing as like our speed, time, distance triangle, or the velocity time displacement triangle. We can use this here because we don't have acceleration. Acceleration changes vertically due to gravity, but horizontally, there's no change in acceleration. It's a constant velocity. So the distance horizontally will just be that velocity multiplied by time. Well, according to our triangle of the initial moment, the x component is 17.3. So we can say horizontal velocity is 17.3, and the total time that it travels horizontally would be the 2 seconds that we calculated previously. So horizontal displacement will be 17.3 times 2, which gives us 34.6 meters. So the ball goes down the field 34.6 meters. For practice, we're going to look at page 43, numbers 2, 4, 5, and 7.